usual, my brain was on the very last point I wanted to make, managing to stumble over something involving the reaction of sodium amide and sodium acetylide. It's an off-the-cuff comment. So there'll be a problem in the discussion section this coming week that's actually going to address this issue in a reaction of, in a slightly different reaction that illustrates the same point. Anyway, I think it'll make things very clear to you. What I'd like to talk about today is Lewis acids, Lewis bases, and their relationship to organic reaction mechanisms. And we'll introduce the concept of nucleophiles and electrophiles that will be central to all of the remaining sequence, the A, B, and C sequence of the organic chemistry course. So a Lewis acid is an electron pair acceptor. And a Lewis base is an electron pair donor. And I'll write an example of a Lewis acid, Lewis base reaction that's probably not so dissimilar to things that you've seen in general chemistry. Maybe one of the molecules is an organic molecule, but maybe you've even seen this reaction before. So let's look at the reaction of boron trifluoride, BF3, and I'll write out the names here. With diethyl ether. They react to form a complex called boron trifluoride etherate, BF3-ET2O or ET2O-BF3. And I'll write out the name of this complex. Now, regardless of whether you've seen this precise reaction or similar reaction to it in the past, what I'd now like to do is to think about this reaction with the same tools that I, and Buck, and Johnny use every day in thinking about organic reactivity, and that is the flow of electrons associated with the formation of bonds. So I'm going to write out a full Lewis structure of boron trifluoride and a Lewis structure of diethyl ether that focuses on the oxygen atom. And I'll try to be good about remembering to draw in all my lone pairs of electrons as, at least at this point in your education, I expect of you as you're starting to get comfortable with writing reactions. So here's boron trifluoride, here's diethyl ether. Drawing my lone pairs of electrons. The boron trifluoride accepts a pair of electrons from the diethyl ether, so it is acting as a Lewis acid. Boron doesn't have a complete octet, except by resonance you can write structures in which it does have a complete octet. But if you write an uncharged resonance structure, it has only or a resonance structure with no formal charges, it has only 6 electrons around the boron. In other words, the boron is unhappy. It wants an octet. The diethyl ether has electrons to share. It acts as a Lewis base. For the sake of consistency, I will not capitalize the word base. Electrons flow from the diethyl ether. The way we write this is we show the electrons flowing from the lone pair. We show our curved arrow beginning at the lone pair, and they go to the boron, they go to the atom. We have, as I showed above, an equilibrium. And now we form our complex, and I'll write it. Doesn't matter which I write on the right and which I write on the left. I'll write it. So the CH2, CH3s coming off the oxygen with one lone pair on the oxygen. Now we have formal positive charge on the oxygen, formal negative charge on the boron. You'll notice that we have not created any net charge. We haven't created any overall charge. We started with 2 uncharged molecules. We end up with an uncharged species. And I'll complete my drawing by being a good person and putting in my lone pairs of electrons on the fluorine. Thoughts or questions? Now, one of the things that's confusing the first time around, talked about different models of reactivity, we talked about different models for structure and bonding. Here we're talking about different models of acidity. Last 2 lectures we've talked about Bronsted acids in various forms. So what's the relationship? The term Lewis acid is just a more inclusive model for acid. In other words, all Bronsted acids are Lewis acids. And all Bronsted bases are Lewis bases. And I'll illustrate this by returning to one of the reactions we had seen before, just a simple reaction of ammonium ion NH4 plus with hydroxide ion OH minus. Let's look at this reaction. The reaction, of course, is an equilibrium to form ammonia and to form water. So what's happening in this reaction is electrons are flowing from the hydroxide to the proton on the nitrogen. That proton is accepting the electron pair, but of course it can't accept the electron pair and have 4 electrons around it. it needs to relinquish 2 of its electrons to nitrogen. And you'll notice how I show that. I show the electrons going from the pair of electrons that comprise the bond onto the nitrogen atom, so that we end up with a lone pair of electrons on the nitrogen, and now we end up with a new bond to water associated with this flow of electrons, or a new bond to hydrogen. So, this molecule here, the ammonium, is acting as a Bronsted acid, because it's giving up a proton, but it's also acting as a Lewis acid because it, or at least the hydrogen on it, are accepting a pair of electrons. The hydroxide, in turn, is acting as a Bronsted base. It's accepting a proton, but it's also acting as a Lewis base. Thoughts? Let's now play with a distinctly organic reaction. And what's nice is you'll start to see that the patterns really are very similar in all of these reactions that we're looking at. So the reaction that we'll look at is the reaction of a tert-butyl carbocation with water. This week's discussion section problems feature a tertiary butyl carbocation. I'll write out the name. These names will eventually start to flow off your tongue. Tert is short for tertiary. Sometimes you'll see it written as just T. Butyl. We write it with a hyphen to show that it's connected, that it's modifying butyl. And carbocation means a cation, a positive ion, that's centered on carbon, hence the positive charge on carbon. And we'll look at its reaction with water. Ultimately, I'm going to show this as part of a bigger reaction called acid-catalyzed alkene hydration. This is one step in the mechanism of acid-catalyzed alkene hydration. But right now, I'd just like to focus on one step, on this Lewis acid, Lewis base step of the reaction, where now our water is acting as a Lewis base, our tert-butyl carbocation is acting as a Lewis acid in this reversible equilibrium reaction. What's happening? Well, as I said, there's fantastic analogy. We're about to form a bond between water and the tert-butyl carbocation. I'll show you how this goes. Electrons flow from the water to the carbon atom. Remember, your lone pair, your curved arrow should start at the lone pair and should end up on an atom. We're forming a bond here, and the resulting product of this reaction is like so. It's protonated tert-butanol. As I said, we're acting here, our water, and I'll come down to the other blackboard, is acting as a Lewis base. Tertbutyl carbocation is acting as a Lewis acid. And really this reaction is the exact same reaction we see on the other blackboard. The tertbutyl carbocation has only 6 electrons around carbon. Boron trifluoride has only 6 electrons around boron. Both of them, both the tertbutyl carbocation and the boron trifluoride, would like to get a complete octet. I talked before about how there are many analogies between water and alcohols, and there are some analogy between alcohols and ethers in their reactivity. Diethyl ether is like water with 2 carbons, 1 on each side. It still has, although it doesn't have an OH group, it still has a lone pair of electrons on oxygen, so it can act like a Lewis base, as we see in this reaction. Organic chemists have special names. I know we have a lot of names here, and they just start to flow off your tongue after you use them and speak them for a while. Organic chemists have special names for Lewis acids and Lewis bases in organic reactions. I think I've mentioned them already. Organic chemists would call a Lewis acid rather, in this reaction, an electrophile. Electrophile means something that likes electrons, right? Philis, I think, is Greek. So anyway, very simply, you have a positive charge on the carbon. You have an incomplete octet. It wants electrons. The Lewis base has electrons to spare, and so we call it a nucleophile. That may not be as obvious, but when you think about it, it makes sense. It likes something with a positive charge. It likes something that's like a nucleus. And so an organic chemist would call, I'll put these in parentheses just to say that we're using one or the other, an organic chemist would say, this is an example of a reaction of an electrophile, a tertbutyl carbocation, with a nucleophile, water. Let us now use this one reaction and use the concepts of acid-base chemistry to look at a complete organic reaction mechanism. We're going to look at the reaction mechanism for acid-catalyzed alkene hydration. Spend some time today talking about this. We're going to go through it very slowly. We're going to look at it both forward and in reverse and see the roles of acids and bases in this reaction. The example that I'll give us is the reaction of isobutylene with water. write out the name of these molecules. We'll get more about nomenclature as we move on to the chapters on alkenes and alkanes. So this molecule is called isobutylene. It's also called 2-methylpropene. Isobutylene is the common name. 2-methylpropene is what we would call the IUPAC name. Isobutylene reacts with water but not if you just mix them, but rather if you have an acid catalyst. I'll write this as H3O plus in H2O. And I'll point out that the H3O plus is a catalyst. As I've said before, you can't go into the stock room and get a bottle of H3O plus. You always form H3O plus by adding a strong acid to water. If I wanted to do this reaction and wanted a catalyst, I would take some sulfuric acid and put it into water, and that of course would make H3O plus and HSO4 minus bisulfate anion. The overall product of this reaction, and it's an equilibrium, goes forward, it goes reverse. It's tert-butyl alcohol. And again, I'll write out the name of the reaction. We're running out of space on this blackboard. I'll write it out here. You'll hear it referred to as tert-butanol. You'll hear it referred to as tert-butyl alcohol. Both of those are common names. You may also see it referred to as 2-methyl-2-propanol. That's the IUPAC name. And is so often the case when I'm just writing out a reaction, when my focus is on reactants and on products, I'm not going to be showing you all of the lone pairs of electrons, and I won't be focusing on formal charges so much, although it's useful to write them in. What I'm doing here is showing the overall reaction. Now what I'm going to do is to write out the 3-step reaction mechanism for this reaction. So let's begin. Here's our isobutylene. Isobutylene has some electrons. It has electrons in the sigma bonds, of course, but most importantly, it has electrons in the pi bond. And for that reason, it can easily act as a nucleophile. It can act as a Lewis base. It can act to react with something that wants electrons. Now, we've already seen examples in which things bearing protons have acted as acids. We saw an example of ammonium, where the ammonium ion donated a proton. We had a positive charge on the ammonium ion, and it was reasonably willing to give up that proton when we had a strong base, when we had hydroxide anion. In this case, this is not a strong Lewis base. The alkene is a weak Lewis base. It's relatively happy. But we do have one strong acid present, and that acid is hydronium ion. We're about to see how the hydronium ion acts as a catalyst in this reaction. We're going to consume it in the first step of the reaction, and you'll say, oh my goodness, we're consuming a catalyst. It can't be a catalyst. And then at the very end, we're going to regenerate it so that no ammonium ion is actually, or no hydronium ion is actually consumed in the overall reaction. All right, here's our hydronium ion. We're all very comfortable with the idea that a hydronium ion is an acid. We're going to show electrons flowing from our Lewis base to our Lewis acid, just as we had done with hydroxide and ammonium. We draw our curved arrows starting at the source of electrons. In this case, it's not a lone pair, but rather a pi bond, another good place for electrons to come from. We show electrons going to our proton on the hydronium ion, and in turn, we can't have 4 electrons around that proton, so we push our electrons back onto the oxygen, giving us water. All of the steps in this reaction are reversible equilibria. We end up with that proton now attached to this carbon atom. So we've gone from a carbon with 2 hydrogens around it to a carbon with 3 hydrogens around it. We have a tert-butyl carbocation. There are 2 more methyl groups that I simply, for the sake of simplicity, won't draw out as full Lewis structures. And finally, we have our water molecule. We've put our lone pair back onto the oxygen atom. That's step 1. Step 2, we've seen over on the left-hand blackboard. I'm going to write it again. Here's our tert-butyl carbocation. Now I won't bother to write the full Lewis expansion of the methyl group because at this point we don't need to concern ourselves with it. Our tert-butyl carbocation reacts with water. Electrons flow from the oxygen atom to the carbon atom, just as we had seen before. We have an equilibrium. And just as I had drawn before, we have our protonated tert-butyl carbocation, our protonated tert-butanol. Doesn't matter whether I draw this hydrogen pointing down or I draw this hydrogen pointing up. In all cases, we're representing the same thing, a tetrahedral oxygen atom, which we just used the vertices of a square to show, or a cross, to show the positions of the oxygen atoms. All right, we're almost at our product. We have just one last thing we have to do, and of course we don't have our catalyst back, and I promised you that you're going to regenerate your catalyst at the end of this process. We're in water. In water, protons flow on, protons flow off. Water can act as a Lewis base. We have lots of water present. Here's our protonated tert-butanol again. We have lots of water. For all intents and purposes, water is a comparable Lewis base to the tert-butanol, or to put it another way, hydronium ion is just about the same strength of Lewis acid as is protonated tert-butanol. We have lots and lots of water present, and so water happily plucks off our proton. Again, we show electrons going from the lone pair to the hydrogen, electrons going back onto the oxygen. Too much, write it out over here. Here's our hydronium ion. Thoughts or questions? And when in biology, so here I said that water, the hydronium ion acts as a catalyst. We proved it in the first step. We regenerated it in the last step. And when in biology you learn about enzymes, it's actually the same thing. In the first step of a detailed reaction mechanism of an enzyme, the enzyme is changed in its interaction with the substrate. And by the end, your enzyme is regenerated and your product is released. And this occurs thousands and thousands of times. And here too, just a little bit of acid can catalyze the formation of thousands and thousands of molecules of tert-butanol.
So in the 3 steps, how do you know where the water is?
How do you know? Well, we're learning pathways and you're going to become more familiar. But what's a good guideline? We have 3 different things present here. Isobutylene, water, and hydronium ion. We think about what's the nucleophile, what's the electrophile. Well, isobutylene essentially can only be a nucleophile. Water can accept a proton. Hydronium ion can give up a proton. That's a degenerate reaction if hydronium ion passes a proton to water, and that occurs thousands and thousands and thousands of times. So in the end, we look, wait a second, the best nucleophile is going to be isobutylene. The best electrophile is going to be hydronium ion. The nucleophile gives its electrons in an acid-base reaction to the hydronium ion, and we start down the pathway. Then we look, we say, wait a second, we have a tert-butyl carbocation. That tert-butyl carbocation is unhappy. It wants electrons. Who has the electrons? Water has some electrons. The water can give the electrons back to the tert-butyl carbocation. And then we're over here, and we say, protons can get passed around. Water has electrons. We have lots of water. It happily takes the proton off. As I said, this is an equilibrium reaction. And what I'd like us to do now is to look at the reverse reaction. Because technically, all reactions that can go forward can go in reverse as well. In principle, some end up going so far to the right that you never see the reverse reaction. The reverse reaction is acid-catalyzed alcohol dehydration. and I'll write out the overall equation and then a detailed reaction mechanism. The overall equation, all I'm going to do is take what's on the right of this arrow and bring it to the left, and take what's on the left of this arrow and bring it to the right. In other words, I'll take my tert-butanol on the left. I'll show my catalyst, H3O+, my solvent, water. Over the arrow is typically where you show reagents, and under the arrow is typically where you show solvents in writing reactions as organic chemists think about them. The left is typically where one shows product or reactant, and the right is where one shows product. So here's our isobutylene, and the other product of this reaction is water. Reactions go by the same pathway in forward and reverse. Organic chemists have a fancy, and chemists in general have a fancy name for this reaction. It's called the principle of microscopic reversibility. And I'll write it out for you. The reverse reaction must have the same path as the forward reaction, or the same mechanism. This makes sense. Reactions take the path of least resistance. They take the shortest path. And if you were to, say, drive from where we are now to, let's say, Balboa Peninsula, what I'd do is I'd get on Bison and go to the 73 and go to the 55 and take the 55 all the way down across the PCH to Balboa Peninsula. And coming back, the shortest path, the lowest energy path, the least resistant path would be the exact same. I would take the road from Balboa Peninsula along across the PCH through Newport, through Costa Mesa to the 55 to the 73 and back here. So we're going to write out the mechanism for the reverse reaction. The reaction ended with the deprotonation of protonated tert-butanol. And so the very first step in the reverse reaction is just going to be the protonation of tert-butanol. In other words, here's tert-butanol. Here's our hydronium ion. The hydronium ion acts as an acid, both a Bronsted acid and a Lewis acid. It gives up a proton to the oxygen atom of terbutanol. We already discussed how this is an equilibrium where protons come on, protons go off. I show the same notation of curved arrows to show the flow of electrons. I have an equilibrium. I get protonated terbutanol and water. Just as in the forward reaction, where the first step, oh my God, we lost our catalyst. Here, in the first step, our catalyst is consumed. In the last step, it's going to be recreated. And of course, the last step is going to be the same. I think what I'm going to do is simply leave these two blackboards up so you can see what I'm writing, and I'll return to this blackboard over here. Yes? Do all of what? The examples today? Yeah. And in fact, acids and bases are so central in organic chemistry that you will see many, many reactions as we get to carbonyl chemistry, where hydronium ion is acting as a catalyst. Of course there are other reactive species. There are hydroxide ion. Heck, we just saw an example with boron trifluoride reacting with diethyl ether. But you'll notice that this theme of species with electrons and species that want electrons, of nucleophiles and electrophiles, continues again and again. Well, that's a good question. What I tell you, you're going to learn it, and you're going to become more and more familiar. We're going to learn about reagents a little bit in this course. Reagents are chemicals that one adds in reactions of organic molecules, and more in the 51B course, the 51C course. And you're going to learn, oh yes, a Grignard reagent reacts with a carbonyl compound, and after aqueous workup with a little bit of acid forms an alcohol. All right, next step of the mechanism. And this is hard because you haven't seen this before. We're learning things that are new. Next step of the mechanism is the exact reverse of the middle step. We have protonated terbutanol. Our protonated terbutanol formed in that middle step on the right-hand blackboard, and now it's going to break apart. It formed from a carbocation and water. In the reverse reaction, it breaks apart to a carbocation and water. Electrons flow from the bond between oxygen and the carbon atom to the oxygen. We have an equilibrium. We generate terbutyl carbocation. Our Lewis acid. And we generate water. Our Lewis base. Now we're headed on the pathway back to our alkene. to head back to the alkane. Remember, we started in the forward reaction, in the very first step of acid-catalyzed alkene hydration, by placing a proton, by having a proton react with the double bond of isobutylene, adding a proton. In this case, we have to take away a proton. And this is the step that students, particularly the first time around, have the toughest time seeing. Going to focus on one of our 3 methyl groups. They're all equivalent. It doesn't matter which one I focus on. I'll focus on the top one. What's going to happen in this step is we're going to lose one of these protons, and we're going to take the electrons that held on to the proton and push it into between the 2 carbon atoms to form a double bond. It makes sense that this would want to happen. It makes sense that this would want to happen because this carbon atom is unhappy. It doesn't have a complete octet, and it will do what it needs to get that complete octet. Later on, you're going to learn about a concept called hyperconjugation, in which you will learn that that carbon atom can beg and borrow electrons in order to feel a little bit less unhappy. I introduced this concept when I talked about the methyl carbocation the other day, and I said, well, you're never going to see a methyl carbocation, they're really unstable, but if you have some more carbon atoms around there, those carbon atoms can donate electrons. If you have some more CH groups around there, can donate electrons. And that's what hyperconjugation is. That's begging, that's borrowing. Now we're going to see stealing. And in going from the terbutyl carbocation, the positive charge is going to steal this pair of electrons from the CH bond, but it will be aided and abetted by a cooperating water molecule. Our water molecule has electrons. It takes the proton. The proton donates electrons in between the 2 carbon atoms. And we get back our isobutylene. And our protonated water and our hydronium ions. And so, in spite of this minor petty theft, all is right in the world at the end. The carbon has a complete octet. Our catalyst, which was taken away at the very first step of the acid-catalyzed alkene dehydration, is regenerated at the end. All right, well, we will pick up next time talking about Chapter 2, talking about alkane, Chapter 3, talking about alkanes,